presentations in Vermont Public Utility Commission case number 21-3883-rule, which the commission opened to develop a rule for energy storage facilities as directed by the legislature in Act 54 of the 2021 legislative session. The commission is hosting this 5-part webinar series in conjunction with the U.S. Department of Energy Office of Electric Energy Storage Program and Sandia National Laboratories. We are conducting this webinar series remotely using the Teams platform. We will be recording these presentations and making them available to the public as soon as we can post them. We will provide information on how to access the recordings as soon as possible, but I should say the first session materials should be up as of today. And the way that you would access those is go to the Commission's electronic filing and case management system, and that can be found at epuc.vermont.gov. And then you need to search by the case number, which, as I said earlier, is 21-3883-rule. And when you get your search results, you'll click on that particular case and it will take you to a page. And what you'll find is under the tab for commission issued documents, you will find a memo that will have a link that will take you to the audio and video recording of session 1. And then if you click on the tab all other documents, you will find that we have posted the slide decks from session 1. If you do experience technical difficulties today, I encourage you to try and reconnect to the platform. Given the large number of attendees, we will not be able to halt the presentations for any one person that is experiencing difficulty with their connection. In the event someone is unable to reconnect, they will have access to the recordings of each session once they are posted, just as I described. Please keep your cameras and microphones off during the presentation. That will help conserve bandwidth and screen real estate. My name is John Cotter. I'm a staff attorney and deputy general counsel at the Vermont Public Utility Commission. I am joined today by Mary Jo Królewski, utilities analyst, and Dominic Gotti, the Department of Energy Clean Energy Innovator Fellow here at the Commission. Before we get started, I would like to thank on behalf of the entire Commission, our colleagues at Sandia National Laboratories that have been working with us to make these presentations possible. Today's presentations will cover part 2 of a 2-part session on the installation and operation of energy storage systems, and will include discussion of the interaction between storage facilities and the grid, metering and charging and discharging of storage facilities, opportunities for sustainability and stability, and an introduction to the Quest software program. Our presenters today will be Mr. Todd Alinsky-Paul, Mr. Atri Bera, Dr. Todd Levin, and Mr. Patrick Balducci. We will also have some introductory remarks from Dr. Emery Jouk. I will now give a brief summary of each of their backgrounds. Dr. Jouk is Chief Scientist, Energy Storage at the U.S. Department of Energy Office of Electricity. He is recognized as an international leader in the energy storage field and has decades of experience leading the energy storage program for the Department of Energy. For the past 2 decades, he has directed the Electrical Energy Storage Research Program in the Office of Electricity, developing a wide portfolio of storage technologies for a broad spectrum of applications. Dr. Jouk has devoted over 3 decades to the innovation and advancement of energy storage technologies, connecting diverse small businesses with federal objectives and resources, with a remarkable record of success supporting development and transition of technologies from early research and development stages to commercial success in the marketplace. Mr. Alinsky-Paul directs the Energy Storage Technology Advancement Partnership, which aims to accelerate large-scale electrical energy storage deployment through collaborative efforts between state energy agencies, the U.S. Department of Energy Office of Electricity, and Sandia National Laboratories. He is also the Clean Energy States Alliance lead for state energy storage policy support, directing CESA, that's the Clean Energy States Alliance, directing CESA's Energy Storage Working Group, conducting independent research and analysis on state energy storage policymaking, and providing direct policy and program support to state energy agencies engaged in developing energy storage policies, programs, and regulation. His recent work has focused on virtual power plants, battery storage as an efficiency measure, the economics of energy storage, and the equitable incorporation of solar and storage into state clean energy policy and programs. Todd holds a Master in Science in Environmental Policy from Bard College and a Bachelor of Arts from Brown University. Mr. Barra is a senior member of the technical staff in the Energy Storage Technology and Systems Department at Sandia National Laboratories. He received a Bachelor of Science degree in Electrical Engineering from the National Institute of Technology, Durgapur, India in 2015, and a PhD in Electrical Engineering from Michigan State University in 2021. His research interests include optimization of grid-level energy storage systems, grid integration of renewable energy resources, energy storage analytics, power system reliability, power system planning, and machine learning techniques applied to power and energy systems. And I should apologize, Mr. Barra, I should be referring to you as doctor, given your educational background.
No worries.
Dr. Levin is the electricity markets team lead in the Center for Energy, Environmental, and Economic Systems Analysis at Argonne National Laboratory. His research interests focus on utilizing advanced optimization and simulation methodologies to model complex interactions in electricity markets and quantify the implications of domestic energy policies and regulations. He also maintains a strong interest in international energy development, examining optimal centralized and decentralized rural electrification strategies, as well as a range of global energy security issues. Dr. Levin holds a Bachelor of Arts in Physics from Northwestern University and a PhD in Industrial Engineering from the Georgia Institute of Technology. And Mr. Balducci is the manager of the Power Systems and Markets Research Group in the Center for Energy, Environmental, and Economic Systems Analysis at Argonne National Laboratory. At Argonne, he also serves as the Lab Relationship Manager over the U.S. Department of Energy Renewable Power Programs and the Office of Electricity Energy Storage Program. Mr. Balducci has led research efforts evaluating the benefits of energy storage at 17 sites across the United States, with combined power and energy capacities of 1.8 gigawatts and 19 gigawatt hours, respectively. And he leads efforts to enhance economic assessment tools for the Department of Energy. He holds a Bachelor of Science in Economics from Lewis and Clark College, where he graduated with honors, and a Master's in Science in Applied Environmental Economics from the University of London, Imperial College of London. We will have a brief opportunity for questions and answers at the end of each presentation. Obviously, we have quite a few folks today and a lot of material to cover. So if we get more questions than time allows, we will be prioritizing questions from those who have been actively participating in the rulemaking process in case number 21-3883-rule. If you do have a question, please enter it into the chat function and make sure to type in your name and your affiliation before you begin typing the question. Please understand this is not an opportunity to express opinions or offer comments. Rather, it is an opportunity to ask clarifying questions in response to the materials you hear today. We will be establishing a schedule for moving the rulemaking process forward after we conclude this webinar series, and there will be opportunities at that time for providing comments and recommendations on what the rule should include. Of course, you are always welcome to file public comments into the case at any time. With all that said, we're going to kick things into gear, and I will hand things over to Dr. Zook. Dr. Zook, please.
Well, hello. It's a pleasure to be here and to be sharing the organization of this webinar series with the Public Utility Commission of Vermont. Vermont is a state with whom I have a lot of personal connection. And so it's very pleasant to be working with Vermont. Today's webinar specifically is about analysis. When we started considering deployment of energy storage in actual facilities, we had two things in mind. One of them is in choosing projects, we wanted only projects that have some innovative feature. That innovative feature could be the technology involved, it could be something of the business case, it could be the financial arrangements that are being made to amortize the cost of the building. It had to be something innovative and novel. Even geography could be innovative if it's in a corner of the country where we have not had anything to do yet. The other thing is we wanted to, once the project was built, we wanted to make sure we have careful analytics of how the project is running, both technically and economically. And in many facilities, people had been traditionally so happy to have it work that they have really neglected doing the analysis, which can help other facilities of a similar kind profit from the experience. So without further ado, we are now going to go into the today's program, which is essentially about analytics in some of these novel installations, of which, by the way, Vermont is full of. So thank you, and we will go ahead with our first speaker, Todd Olinsky-Paul.
Great. Thank you for the introduction, Imre. I am happy to be here. I assume everyone can hear me and see me. If not, please let me know. And I understand that I'll be sharing my screen, so let me do that now. Yeah. Hopefully you can see the slide. If not, somebody please let me know. Again, happy to be here. Of course, I'm based and working and living in Vermont. I wasn't expecting to do this today, but Waylon from Sandia unfortunately couldn't be with us, and I'm sort of pinch hitting. So hopefully this will be useful. This is what I'm going to present here is a framework for states to conduct benefit cost analysis for battery storage incentive programs, essentially. And this is something that we've been working on for quite a while. We have a report out in late 2022, so just about a year ago, summarizing our work in this area, and this presentation will summarize the findings and recommendations from that report. So let me start by just introducing CESA, Clean Energy States Alliance. If anybody is not familiar, we're based here in Vermont. Our offices are on State Street in Montpelier, but we work across the country. We are essentially a membership organization for state energy agencies. We're a nonprofit, and we help our members, those state agencies, conduct their work. Here are some of our members' logos, so you can get an idea. Vermont is a member. And I also want to mention that one of the things that we do, among many other programs, is to work on the Energy Storage Technology Advancement Partnership, or STAP. This is conducted under contract with Sandia, with funding from US DOE Office of Electricity. You can see Emery there in the photo, and myself and some other folks at a ribbon cutting that was in New Mexico last year. This STAP program essentially does three things. It facilitates partnerships between states and Sandia and DOE and other partners like utilities to develop energy storage demonstration projects, such as what Dr. Zook was just referring to. STAP also provides support to states in developing energy storage policies and programs. And we also disseminate conference presentations and so forth. So when we're talking about energy storage benefit cost analysis, we kind of need to start from basic understanding that there are two types of benefits: monetizable benefits and non-monetizable benefits. So this is very important for energy storage in particular because it's still a technology that is relatively new. And when I say relatively, I mean relative to the markets that exist for energy services and programs that exist for energy technologies and services. So because the markets haven't entirely caught up with the technology, a lot of the benefits that storage can provide are not yet monetizable markets. So for example, if you are using battery storage to reduce peak energy demand, well, that's monetizable. You can engage in demand charge management behind the meter if you're a commercial facility and reduce your energy cost. If you're a utility, you can reduce your peak demand and thereby reduce your capacity costs and your transmission costs. So those are all monetizable. On the other hand, if you are, for example, deploying to increase resilience on the grid, well, that's a benefit. Everyone recognizes resilience is important. We lose billions of dollars every year to power outages. This is an extremely important benefit, but it's very hard to monetize. It's hard to see how you can get from installing storage for resilience purposes. You don't know what kind of savings you might realize. There's no sort of market into which you can bid a resilience service. So that's a non-monetizable benefit. The important thing here is that both types of benefits have value. So whether it's monetizable or not, it still has a value. And when we look at benefit cost analysis, it's important to consider all the costs and all the benefits. And the problem is that when you look at storage having lots of non-monetizable benefits, those benefits tend to get left out of the calculations. So we know how to value some benefits better than others. And so it's easy to put the monetizable benefits on your cost benefit sort of balance scale, but it's also unfortunately easy to leave off that you don't know how to monetize and you're not sure what the price should be. So we need to understand that value doesn't equal price, and that failing to assign values to non-monetizable benefits is the same as assigning them a value of zero. In other words, when you do a cost-benefit analysis or calculation, and this is usually done when you are looking at whether to adopt new programs and policies. You want to know whether your tax money, your tax money or your ratepayer money is being spent wisely. So you do a cost-benefit analysis. If you don't assign a value to those non-monetizable benefits, then they default to zero in that analysis. So a low estimated value is better than no value at all. So here's some examples from Connecticut. Connecticut adopted an energy storage incentive program in the course of doing their due diligence and analysis. They ran 5 different benefit cost tests to see how this proposed program would come out. So there are several things you might want to note here. First of all, there's more than one benefit cost analysis or test that can be applied, and different states use different tests. At different tests, the reason they're different is that they look at different benefits and different costs. So, for example, the second one here, the PCT, participant cost test, looks at a fairly narrow range of costs and benefits, whereas the one on the left, the program administrator cost test, looks at a much wider range of costs and benefits. And you can see each cost or benefit here is a different color in these bars. It's easy to see how the test that you pick is going to determine what is considered and what is left off the table when you're looking at benefits and costs. The other thing that's interesting to note here is that they did these 5 tests, and that energy storage program they were considering passed all of the tests. So anything over a value of 1 here means that you're getting a greater benefit than you're paying in costs. So on the societal cost test, for example, the third one from the left, you can see that for each dollar you invest, you're expecting to get about $2.32 in benefits back. So that's a pretty good outcome. Nevertheless, every state is different, every program is different, and so by and large, you want to run your own test with your own inputs and assumptions. And so it's nice to see that storage can do well in these tests, but that doesn't take the place of doing the test for the specific program you're considering. So with all that as background, we thought, gee, wouldn't it be nice if there were a set of best practices or recommendations for states to consider when conducting benefit cost analysis for distributed battery storage programs. And so we contracted, my energy group contracted with the Applied Economics Clinic and asked them to do some research into these various tests that are used in various states, look at benefit cost analyses that have been completed in various states and by utilities and by companies, look at outcomes, and come up with some recommendations. So the method, AEC, Applied Economics Clinic, reviewed 29 battery storage benefit cost analyses that have been completed, looked at the methodologies used and related analyses, and the sources included utilities, utility commissions, state energy agencies, green banks, and research groups from around the country. Now, I should say that the results of this are not tailored for Vermont or for any other specific state. They're really meant to be a generic set of best practices. So keep that in mind as we go through this. Every state, as I said, is different, and you're going to have different requirements. Having done this review, AEC examined these sources, and they looked at benefits, costs, or avoided costs. They looked at values calculated for those benefits. They looked at methodologies used in different BCAs, like cost effectiveness tests, discount rates, and sensitivity analyses. And they looked at the stakeholder engagement because the process here can be very important as well. And then they came up with a set of recommendations. So we're going to go through those recommendations. Start with the cost effectiveness tests. As I stated, there's a bunch of them that are used commonly by various states. And you can see here in this table a summary for each type of test as to what are the benefits that they typically consider and what are the costs that they typically consider. So the recommendation is to use the societal cost test, the SCT, as the primary test, and then the UCT, which is the utility cost test, and the RIM, which is the ratepayer impact measure, as secondary tests. Now, I just want to note here, the societal cost test considers the largest range of benefits, and that was the point I was trying to make earlier. We really don't want to leave benefits off the table. So if you look at the benefits on the left side, left column of this table, you'll see quite a few benefits included in the SCT. Now, the UCT can be important as well because it considers costs and benefits from a utility perspective. So if the utility is charged with implementing an incentive program, for example, that can be an important test to look at as well. The RIM is important because that tests for whether costs are being shifted from certain ratepayers to other ratepayers. So it's not only important to make sure that the program you're considering is returning more benefits than it's costing. It's also important to understand whether the costs are being equitably or evenly allocated, or whether this program is going to shift costs around. And so that's an important consideration as well. I mentioned discount rates. Discount rates are a little complex. What the report recommends is that two different discount rates are used for different purposes. And I want to explain first here that the discount rate is the interest rate used to determine the present value of future costs or benefits. So if we're saying that if we do this now, 20 years from now, we're going to have less carbon going into our atmosphere, for example, and that has a value. So what is that value 20 years from now worth now? And that's what your discount rate is going to help you determine. So there are social discount rates, and then there are financial discount rates. We're recommending using a social discount rate for these are usually, well, I'll get to this in a second, but social discount rates are generally used for longer horizon costs and benefits. Financial discount rates are usually used for shorter term things like the cost of capital. And so you can use a utility's weighted average cost of capital for a financial discount rate and use a social discount rate for other aspects such as longer horizon costs and benefits from the program. So here's a little summary of what each of these entails. But again, social discount rates are usually used to value costs and benefits in 10, 20-year increments, even hundreds of years into the future, while financial discount rates are generally represented by a weighted average cost of capital. It reflects the cost of financing, and this has to do with, for example, what utilities need to consider if they're an investor-owned utility. So I'll leave it there for this topic. Again, if you need to get down in the weeds on this, I'd be happy to answer questions, and I can refer you to the report, and which has a lot more detail than I can get into right now. Benefits. So benefits to be considered. AEC came up with a list of 25 benefits of battery storage, and these fall into various categories. So there are consumer benefits, such as lower ratepayer bills, lower customer energy use, etc. There are avoided system cost benefits. This includes things like avoided capacity costs, avoided transmission and distribution costs, and ancillary services costs. There are environmental benefits, such as reduced land footprint. If you are displacing, for example, peaker plant services by deploying battery storage, and you're able to put the battery storage into existing facilities, then obviously your footprint there is pretty much nothing, as opposed to a peaker plant's footprint. There are grid reliability services, things like reduced power outages, avoided emergency calls, and so forth. And then there are difficult to monetize benefits. These include participant non-energy benefits and societal non-energy benefits, such as public health and environmental justice benefits. Again, you're going to have different benefits considered in different tests. You may be able to pick and choose and decide which benefits you think is you think would be appropriate to consider. And the recommendation here is to include as many of the benefits as you can, even if you aren't sure if there's not a price signal, you're not sure what the value is. It's still important to include those benefits as well as all the costs. So the costs. The basic recommendation here is to use up-to-date battery-specific engineering references to establish correct program costs. Now, there's different kinds of costs. There's administrative costs, capital and labor costs, program operation costs. I won't get too much into this. The cost side is usually a lot easier to quantify than the benefit side because we know what labor is going to cost and what administration is going to cost and so forth. It's a lot harder to figure out how to value, for example, environmental justice benefits, but it's important to try. Okay, sensitivity analysis. A battery-related benefit cost analysis should conduct several sensitivity analyses for two things. One is model calibration, which is to fine-tune the model results based on adjustments to input assumptions. And the other is the full model results to capture uncertainty. And so sensitivity analysis is basically telling us how sensitive your analysis is to assumptions that you're making and allows you to sort of weight various inputs and so forth. And finally, the stakeholder process. It needs to be inclusive, diverse, and equitable. It needs to be a start to finish stakeholder process during the benefit cost analysis. And it should include representatives from a wide range of stakeholders. I won't go through the whole, but this is important because it can really help to identify battery performance information data, market drivers, deployment barriers, develop appropriate peak load forecasts, costs and benefits, et cetera. The more voices you have at the table, essentially early on, the better off you will be. So here's a summary of the recommendations. I won't go through this since I just did. And I will just pause here for a moment to thank Dr. Zook and Waylon Clark for making all of this possible. And I'm sorry Waylon couldn't be here today and you had to listen to my pitch hitting presentation. And that's the end of it. So thank you so much. The report is available at the CISA Resource Library. As are all of our reports, webinars, and other products. And I'll be happy to address any questions. I'll stop sharing at this point.
Great, thanks for that, Todd. Looking at the chat, it doesn't look like, oh, we got one that just came in. Funny as that is. All right, so we got one question for you from Vijay Vankayala from the British Columbia Institute of Technology, who asks, very helpful list of benefits. One of the confirmed benefits of storage are local resilience, which is a monetizable benefit. Did the study distinguish reliability from resilience benefits? Follow-up question, some jurisdictions are considering expedited processes based on selected benefits with weights. Any comments on that?
I'm not sure what the expedited process based on selected benefits with weights is referring to exactly. I will say that I believe that the study did distinguish reliability from resilience. Reliability is a system benefit generally, whereas resilience may be a benefit for the host facility or the community where the resource is placed. So those are generally two different things. The utility may see in reliability of the grid, for example, fewer emergency calls, things being able to be restored faster or not going down during natural disasters. And that's a little different from the benefit you would get, for example, if you have a business and you're able to continue to operate through a grid outage because you. So that's about the best I can do. I don't know in terms of expedited processes. I can't really speak to that. I would have to speak to it on a case by case basis. I'm not really prepared to talk about it in general.
Great, thank you, Todd. I got another one for you from Craig Keeney from the Vermont Electric Cooperative, who asks, "What do we do if the societal cost test points one direction, but the UCT or RIM points in another?"
Yeah, hi, Craig. Well, as I showed, the different tests really are looking at different things. And so I think you have to take into consideration um, what's your primary test. I mean, and that should be based on what's important and what do we want to measure. I mean, we're looking at the SCT as the recommended test because it takes into account most of the largest number of societal and social benefits that storage can provide. We want to make sure that we include those in the test. Um, as I said, the rim really is important, in my mind at least, because we want to make sure that we're not simply shifting costs from one group to another. So if we're saying, yes, we're getting a good return on the investment based on the SCT, but the rim is saying that we're shifting costs, then that's not saying we shouldn't do storage. It's saying that we should do storage, but we should figure out how to do it in a way that isn't um, uh, penalizing certain groups of ratepayers by shifting costs around. So what that's saying is, we need to look at how we're doing things and maybe figure out a more equitable way to pay for whatever it is that we're trying to achieve. And the UCT, I think, again, this is specifically looking at the utilities costs and benefits, um, and that should be addressed by the regulator, looking at how the utility is able to, uh, you know, get compensated for investment. That also doesn't say we shouldn't do storage. It says that maybe we should look at where the money's coming from to equitably pay for things. I hope
Sounds
that's
great.
helpful.
Great. Yeah. Thank you so much, Todd. I appreciate that. And again, I want to give you another round of applause. Thanks for stepping in and, giving such a wonderful presentation for us here today. Um, it looks like you're out of questions right now. So I want to take this time and go ahead and pivot to our next speaker, Autry Barra. Autry, are you on the line?
Yes, I
Hey, there
am.
you are.
Can you see and hear me?
I can.
Okay,
Looking
great.
fantastic. Awesome.
Thank you.
And you're okay to share your slides?
Yes, let me do
Perfect.
that real quick.
Sounds good. I will hand it over to you. Take it away whenever you are ready.
Okay, I would preferably keep my camera off during the presentation. My internet connection is not that reliable here. So just to make sure we don't have any interruptions. Um, so good afternoon, everyone. Okay, now my slides are full screen. Let me know if you have any difficulties viewing the slides. So I'll talk about Quest today. Initially, Toon Nguyen, who's the lead for this project, he was supposed to speak, but he couldn't make it today, so I'm filling in for him. So this is the outline of what I'm going to talk about today. I'll give a brief introduction of what Quest is. I'll talk about the models behind Quest, which includes energy storage applications, technology selection, different valuation applications that we have for Quest, and then I'll talk about the tool itself. So what is Quest? Quest is an application suite for energy storage simulation and analysis developed by the Energy Storage Systems program at Sandia National Laboratories. It is typically used for energy storage valuation, technology selection, evaluating storage performance, and grid planning with storage, and it is ideal for planning and analytics purposes. So I'll talk a little bit about energy storage applications first. We typically categorize it into two categories: power and energy applications. For power applications, we generally demand a huge amount of energy in a really short time from the storage. Those are the power applications. Some of the more common power applications are frequency regulation, voltage support. So I'll talk a little bit about each of these applications first. Frequency regulation is due to the constant variation in load and sometimes generation, the frequency of the grid fluctuates continuously. So we have to regulate that. We have to keep it as close to the nominal value of 60 hertz. So we can use storage to do that, to the regulation. Then voltage support. We also want to keep the nominal voltage of the system close to the 1 per unit value, and storage helps with that. Then there's small signal stability, where if there are small disturbances in the system, the storage can step in, provide active power and balance that out. Then renewable smoothing, the storage helps in mitigating the variability of renewable resources like wind and solar. Then there are the energy applications where we ask the storage to provide us with energy for a long period of time. And energy arbitrage is one of those where you recharge your storage during periods of low demand when the cost of electricity is lower, and then during periods of high demand, you discharge it. Renewable energy time shift, let's say you have a solar plant or a wind plant where um, you have excess generation at a certain point of time, and you can store it at that time using storage, and then during periods of high demand when there's a deficiency, you can discharge your storage to make up for that. Then there's customer demand charge reduction. We have some utilities charge demand charge during peak demand periods. So if you have a storage in your home, you can use it to keep it charged when you have low cost of electricity, and then discharge it and reduce your demand charge. Transmission and distribution upgrade deferral. Sometimes it's not economically feasible, or we have other issues for building new transmission and distribution lines. So we can use storage during that period. We can also categorize energy storage applications as front of meter, behind the meter, based on the location of the storage in the grid. In the figure in the right, you can see that there are several behind the meter applications like time of use bill management, demand charge reduction, PV utilization, and backup power. Then front of the meter, we have frequency regulation, arbitrage, capacity market, spinning, non-spinning reserve, black start, and then some applications fall under both categories like T&D deferral, congestion relief, power quality, reliability, and resilience. So how do we go about doing the techno-economic analysis of energy storage? The first step is to identify revenue streams. What are the possible services or applications that an energy storage can provide in a particular market? Then we select the right energy storage technology to provide these services. Then we evaluate the overall economic benefits given the limits in performance of the selected storage technology. One of these is the energy storage selection. So um, the goal is given a set of user inputs, we perform an initial screening to identify and rank feasible energy storage technologies for a given project. For example, the user input might be the grid location, application, system size, and discharge duration. And when we have these user inputs, we look into the energy storage technologies database that we have. And currently, as you can see, for the technologies, we have several electromechanical storage systems like pumped hydro storage, compressed air energy storage, flywheels, and then we have electrochemical batteries, sodium batteries, zinc batteries, flow batteries, lithium, nickel, lead batteries. So we look at different parameters of these different technologies like discharge duration, round trip efficiency, cycle life, depth of discharge, response time to full power, cost, maturity level of the technologies. We also look at the applications database, where there are several parameters like minimum discharge duration, minimum response time, power and energy application, deployment location restrictions, which is specific for the applications. Then when we have looked at everything, we filter out the technologies that are not suitable for the selected grid location or do not meet the minimum application requirements. I'll give you an example here. Let's say you want to do frequency regulation. So pumped hydro storage is not a good option for that, because for frequency regulation your input signal is constantly varying. You one moment you the signal might want your storage to discharge, the next moment it would want it to charge, and even while charging and discharging, the amount of power it wants every time period would vary constantly. So pumped hydro storage systems, they can output at a fixed value, so those are not ideal for this kind of applications. So this particular Quest application, it filters those out, and then of the remaining technologies, it scores each feasible energy storage technology based on several factors like application requirements, location requirements, cost, and technology readiness level, and it ranks them according to the scores received. These final scores are calculated as a weighted geometric mean of these individual scores, and the user can also put higher or lower weights to these factors based on the importance that they put on those factors. Another important application that Quest can do is energy storage valuation. Um, so, given an energy storage device and an electricity market with a certain payment structure, how would the device maximize the revenue generated and provide value? And Todd mentioned a lot of the factors that we should consider. So, right now, Quest only looks at the different market parameters when we just calculate the revenue provided from the market. So this equation here, or this expression, this is the objective function. This is the total revenue that a storage system can generate from a certain market. This is an example, and in this example, we consider uh, two applications, energy arbitrage and frequency regulation. And this particular example market, the regulation, frequency regulation is split up into two separate products, regulation up and regulation down. So you see three separate expressions here. So we try to maximize this revenue from the market. And there are several constraints that we have to put into place. First is the state of charge constraint, where we track the state of charge of the storage at every time period. If the storage discharges, then we reduce the state of charge. If it charges, then we increase it. And we also put in state of charge limits. So we don't typically discharge the storage system completely or charge it to 100%. One of the reasons for doing that is we try to um, kind of keep the depth of discharge low. So we have seen through experiments and other evidences that the higher the depth of discharge is, the the shorter the lifetime of the battery is. So we kind of try to limit that. And then there are power and energy limits, where um, these are related to the physical constraints of the battery, where you cannot charge your battery entirely in 1 hour. So there is a power limit to that. So we impose that constraint here as well. There can be other constraints, such as requiring the final state of charge to equal the initial state of charge, or reserving enough energy capacity for reliability or resilience applications. Um, we can stack up. Here I show only two applications, but we can stack up more applications. We just need to design the algorithm carefully for the control of the storage. And these also vary based on market and available value streams. Another application Quest can do is behind the meter. In the previous slide, we were talking about front of the meter applications, more market driven, or revenue maximization from the market. Here is what if I, as a residential customer, what if I have my own storage device? So here also there's an objective function, but instead of maximizing revenue from market, we try to minimize the electricity bill of a customer. Um, and these CE, CN, and CD, they correspond to the energy charge, demand charge, and the net metering charge. And similar to the previous application, here also we need to constrain the storage operation with the state of charge constraints, charge discharge limits, etc. There are two other applications that I'm going to talk about or briefly mention. One is the Quest equity, and the other is the Quest performance, system performance. So for the first one, the problem statement is, if given a peaker loading profile, what are the optimal sizes of PV and storage for 1:1 replacement of that plant, and what are the benefits for the environment? So this tool, the Quest Equity tool, is currently under development. We have an alpha release, but we have not released to the public yet, but it will soon be out there. And then for the performance, it's already a part of Quest. You can use it right now if you want. So here, given a charge discharge profile of a battery energy storage system, how much energy is needed to run the HVAC that maintain system temperature within its operating range? What is the optimal size of the storage considering the HVAC load? These are some of the things that we try to answer with this particular application. So now that I have explained the models behind Quest, I'm going to talk about the tool itself, the platform, the graphical user interface, etc. So there are two versions of Quest right now. One is this, or I'd say one version, but different installation processes. So one is a very user-friendly, hassle-free installation where you just go to our GitHub repository and you can download a zip file. And if you extract the executable from there, you just double click on it and then you land on the home page, and that's about it. And then you can use the tool whichever way you want to. And for power users, you can use it if you are proficient in Python and you want to customize the programs, you want to add more features to the already existing code base that we have, then you can do that too. And there is a library, Python library what we are working on. That is coming soon as well. And a little history, the version 1.1 was publicly released in September 2018, and current version is 1.6, which is available on GitHub. I believe that this link is not up to date because our entire repository was moved to the Sandia Labs repository. We don't have a separate SNL Quest repository anymore. I'll update the slides before Dylan uploads that into the website. So what are the current applications that Quest supports? I've already talked about this a little bit, but in the GUI, you can see all these different applications. Quest Data Manager. So this manages the acquisition of data, which can include the ISO and the RTO data, and also utility rate structures, PV profiles, load profiles, etc. And Quest Valuation estimates potential revenue generated by storage by providing ancillary energy services in the markets. We have Quest Behind the Meter that estimates the cost of savings for time of use, net energy metering customers, Quest Technology Selection, and then Quest Performance. And the next releases would be Quest Equity and Quest Microgrid, where you should be able to size storage if you have a microgrid for reliability applications or voltage support and several other things. These are all currently being developed. So this is how a typical Quest workflow would look like. First, you decide what type of analysis you want to do. It can be evaluation or behind the meter or others. So, and then you have to grab the appropriate data from Quest Data Manager, the RTO utility data or PV and load profiles, and then you select the application from first step and you use the data to run your analysis. This is a small example. So this is on the left is the data manager screen where we have options for the different markets: RCOT, PJM, MISO, NY-ISO, ISO NESPP, California ISO. You choose whichever is of interest to you, and um, then you go back here. I think we are in the valuation application now. There are several such screens. We have shown one screen as an example where you can choose what kind of battery you have. You can choose between the different preset batteries, or you can define your own parameters using these boxes. And once you have set all the parameters, you have put in all the inputs, then you can run your analysis, and you'll see the results in a different screen. Here is an example where we were evaluating a storage or the revenue from the storage for regulation and arbitrage applications. And here are the results. So you can split the results in terms of applications by month and also participation percentages. Then an example of a BTM application, behind the meter application. So first you choose a rate structure. Here we have shown as an example the PNM, which is the local utility in New Mexico, PNM residential time of use structure. And then similar to the previous example, here we have you can input your own storage parameters, and then you run the analysis, and it will give you your bill comparison, total bill with and without the ES, and you can compare the numbers. And I believe you can also look at the demand charge comparison, energy charge comparison, and other parameters. And another interesting thing, very useful, when you click on this generate button, you can generate PDF reports, which will have all sorts of analysis, detailed description of the models. Also, you can print through your PDF. So those were some examples, and currently Quest is undergoing a large overhaul. We are moving towards Quest 2.0, which will be more like a software platform rather than one solid software. This can be comparable to an app store for Apple or Android phone, where you install only the applications that you need. You don't install the whole software. So if you just need to do technology selection, you install that, or performance, you install that. There are several reasons why we are moving to this structure. The Python platforms we were using in the past were not that good. We are moving to better packages now, and also we through our experience we understood that it's better to separate out all the applications. It just makes the app more user friendly and glitch free. So like I mentioned, the app hub would work more like an app store that provides access points to multiple apps. Then we will also have a workspace um, where you can use multiple apps, and then you can sort of build a pipeline using the different applications. Let's say you need to select the technology, and then you do a performance or a storage evaluation. Then you can build a pipeline using multiple two in these two apps, and then get results for that. And we will also have a Quest GPT, which will be similar to ChatGPT, that can be used for data analytics and characterization and visualization of large data sets that you might want to input into the Quest tool. So yeah, this is how your app store would look like, or the app hub would look like I mentioned in the previous slide. And this is kind of the workspace. I'm not going to get into the detail of this. So with that, I have arrived at the end of my presentation, and as always, we are grateful to Dr. Juk for his continued support. And we have a pretty big Quest team here where the lead is Tu Nguyen, and we have Jay, Andres, Jeb, who are platform developers, and tool developer. Besides me, we have Cody, Walker, David, Ujwal, Will, and John. Thank you for listening. If you have any questions, I'll take those. I'll try to answer your questions as much as I can, and if I'm unable to, then I'll forward those to two who will respond to those by email.
Fantastic. Thank you so much for that presentation, Autry. Yes, Quest is such a fantastic tool. I'm glad you got to share it with us. Looks like
Thanks.
I got one question in the chat for you so far from Vijay Venkayala from the British Columbia Institute of Technology, who asks, wow, looks like a great tool. Is hydrogen to grid included in storage tech options analysis? Apologies if it's a little off topic.
Hi, Vidya. No, it's not off topic. It's a great question. Currently, we don't have hydrogen to grid in the tool, but it's very easy to incorporate that, and we are working on incorporating new technologies all the time. So we will definitely look into that and include that in the future editions of this tool.
Great, thank you so much. Looks like that was the only question in the chat so far. I want to give a minute to let people kind of catch up with their typing. Planning team, was there anything that you had questions about that we could come off mute and ask too while we wait for another question? All right. Well, Audrey, thank you so much for that presentation. Again, um, really good stuff. And everybody, feel free to reach out to Audrey and to regarding this if you have any more questions. But in the interest of time, I believe we have Todd Levin already on the call. Todd, are you with us?
Yes, I am. Thank you.
All right. Well, I'll hand it over to you.
Okay.
Feel free to share your screen, and the floor is
Give
yours.
me just a second to get that pulled up here. Oops, sorry, that was the window. Nope. Sorry about that. Let's see. It's wanting to share. There we go. Okay. Step into this. All right. Is that coming through okay?
Yeah, looks
I'll
good.
assume
Thank
it
you.
is, unless. All right, great. So thanks everybody. Yeah, I'm gonna talk through a couple of ongoing activities. My name is Todd Levin. I'm the electricity markets team lead at Argonne National Laboratory. I'm also being called in to pinch hit a little bit here. So I hope this presentation is useful. It's going to provide a little bit of an overview of some different energy storage activities at Argonne in the context of the role of kind of understanding the role of energy storage in supporting electricity system decarbonization. So we have a few different studies, a few different methodologies we're working on, and some preliminary results that I can kind of show to demonstrate the direction we're headed, and some final results as well for a few studies. So let me get into it. So the kind of background and motivation behind a lot of this work is summarized in a paper that we just put out in Nature Energy, Energy Storage Solutions to Decarbonize Electricity. And we categorized a number of challenges and opportunities related to capturing the value of energy storage in the types of traditional capacity expansion and production cost type tools that are used to inform system planning, IRPs, and that sort of thing. So, there've been a couple people talking today about specific storage valuation methodologies and services that are or aren't valued. And those are great, but sometimes those more specific storage-oriented tools aren't necessarily incorporated into big picture planning processes. So this paper gets at some of the challenges that need to be overcome to make sure that storage is properly valued in those processes. So highlighting a couple of kind of different potential futures here, the challenge and the role of storage. Higher wind and solar penetrations kind of linked with zero fuel cost resources create some opportunities for storage, but again, maybe aren't always captured in our traditional models and tools. Sector electrification means changing load profiles, which also create opportunities for storage, as well as climate risks and issues around resilience and restoration and operating under extreme conditions. So these slides have a little more information. I'm not going to go through all of these in detail, but maybe just highlighting a couple. Increasing importance of state of charge management. So understanding kind of the opportunity costs associated with dispatching storage units, now versus withholding storage capacity for the future. Look at the impacts of how operational strategies impact the long-term degradation of storage. And kind of interactions with other technologies, or some things on the technology side. On the system side, and I'm going to talk a little bit more about this in some of my future slides here, making sure that you're capturing appropriate both geographic and temporal resolution to really get at the value, the localized value of storage, and the temporal, sub-hourly potentially value of storage, in balancing that those dimensions aren't always captured in traditional modeling. I'll talk later about improving weather and climate data to make sure that you're kind of capturing future conditions and also the volatility, again, where that creates opportunities for storage. And then on the policy markets societal side, decarbonization targets, obviously, it's a big undertone to a lot of the work we're doing. Nearly 75% of Americans are served by an electric utility with at least a soft or voluntary target to decarbonize fully at some point in the future. Well, what is the role of storage in enabling that future? A lot of those targets or standards don't explicitly incentivize or support storage, but there's of course certainly a role there. So what's the intersection between storage and those policies, and how do we capture that value in models? Similarly, the role in competitive wholesale markets and capturing, making sure that the service value is monetized. Some issues around heterogeneous policy landscapes where you have different state policies that operate within a single system, and how do you kind of square those, or there might be some inconsistencies that create challenges for how the system is operated. All right, so I'm going to now just step through. This will be a little bit of a quick run through, but a couple of ongoing activities. So we have one study that we're working on currently to look at the role of storage, and particularly longer duration energy storage, in the national decarbonization or deep decarbonization pathways. To this end, we're using a tool at Argonne called the Argonne Low Carbon Electricity Analysis Framework. This is a highly flexible tool. It has access to a national database. We can zoom in on certain areas or zoom way out and kind of control both the temporal and the geographic resolution very flexibly, as I highlighted before. And at its core, it's comparable to a traditional least cost capacity expansion and production cost tool, similar to like a Plexos or ProMod, for those who are familiar with those commercial tools. But we control the source code, so we can look at things a little bit more flexibly. So what we are doing is looking at a couple of different decarbonization pathways, kind of broadly looking at two different dimensions. So the technology costs, and then the public acceptance of sort of land use. So what that does is it affects the ability to have a transmission expansion, and also limits the availability of wind and solar capacity, assuming higher or lower tolerance for land use for decarbonization. And so what showing here, I put a big preliminary tag on this because this is still very much a work in progress. But kind of what we're getting at, and we're actually going to expand the number of scenarios, and things will change a little bit. But the key thing to highlight the trend that we're seeing is that if you're limiting the amount of land that can be used for transmission expansion for wind and solar, it creates more incentives for storage. You're not able to transport energy as freely. Maybe you can't put as much wind or solar capacity in the really high availability regions as you would like, and so there's a much more benefit to having kind of that localized storage to provide transmission-like services. Similarly, kind of looking at the role of storage, I guess, as you get deeper and deeper decarbonization, we have a couple scenarios. No reduction, no firm cap on national emissions, and then going to like a 90% reduction based on, I think this is kind of the standard 2005 baseline, or 100% reduction. And you can see, especially going to that last 10%, you see a greatly increased role of storage under these four different cases. Even more so, limited land use, low cost, you see much more, and kind of, decreasing from there. But this last 10%, and there have been other studies that show similar effects, it can be very challenging to accomplish that last 10%, and there's a significant role for storage in helping to achieve that. So again, this is work in progress. We're hoping to finalize and publish soon. So keep an eye out for final results coming there. Another thing I highlighted that is important is higher fidelity, potentially temporal fidelity capacity expansion modeling. And again, this is really looking to capture chronological hourly implications. So every hour in a day, for example, rather than some more traditional methods might just sample a subset of hours. in a day or over the course of a year, and even looking at sub-hourly dispatch intervals. So again, this work is actually is finalized. It's currently under review and revision and should hopefully be published soon. There is a preprint available online for those who are interested on SSRN. And so what we did here is we looked at impacts of the temporal sampling and how that affects the perceived value of storage in a model, both in terms of the number of days that you're considering to represent the entire year, as well as whether you're considering hourly or 5-minute dispatch intervals. And again, we used ALEAF, our in-house modeling tool. So a couple of quick implications that maybe show that are relevant for storage. So as you increase the number of days that you use to sample the entire year, the key finding here is that there's a fair amount of volatility in your optimal least cost expansion portfolio for lower numbers of days. And notably, there can be a fairly large jump when you add a new day, a specific new day to the system that has certain operating parameters that weren't captured previously. These results aren't global. They won't apply universally to every model or every system, but we do think that some of these trends and kind of the volatility in when you're using lower temporal fidelity modeling is important. So the kind of key takeaway here is that modelers and decision makers should do some sensitivity analysis around how they're representing the temporal dimension in their modeling. And contrasting this, we ran kind of a null case, and if you want to call it that, in a very hypothetical, entirely thermal system with no solar or storage. And the takeaway here is that those systems are much less sensitive to your number of days, how you represent your year, and both the number and the choice of days. And so again, the messaging here is that methods that we have traditionally become accustomed to using for those thermal-dominated systems are becoming less appropriate in systems with wind, solar, and storage. Similarly, we looked at the impact of representing 5-minute dispatch intervals instead of hourly dispatch intervals. And what that means is that you're actually capturing this sub-hourly, it's primarily solar volatility and uncertainty in your models, which again creates opportunities for storage, balancing needs from storage. And these models are much harder to solve, so we were able to include fewer sets of representative days. But we kind of found this universal trend that when you're looking at 5-minute dispatch as opposed to hourly, there is more storage being built in the system to help provide that sub-hourly balancing, and slightly less solar capacity is built, and storage is kind of filling in those gaps, helping to balance the volatility. So I think that's an important finding. It's not always practical to conduct or consider 5-minute intervals in your capacity expansion modeling, but it is I think an important consideration for folks who are doing these types of studies. And then this figure just demonstrates kind of some of the logic behind that. So this is just a single day, or a portion of a day that we picked from the model that the time periods that were considered. And you can see on the top, this is the hourly dispatch, and this is the 5-minute. So there's a fair amount of alignment, but you can see kind of looking in the middle of the day, there's some hours where when you consider 5-minute intervals, there's both charge and discharge for storage in the same hourly interval, and that kind of gets washed out in the hourly representation. And kind of similar here, you have this little solar peak where, I guess kind of the same effect, where you're charging here and then, dispatching your storage later in the hour. And then if you're looking at just hourly resolution, that kind of averages out to a net discharge, but you're missing some of those ups and downs and some of those opportunities. So again, just to kind of demonstrate the logic behind the result there. Okay, the last thing I want to touch on is our work on climate-informed capacity expansion, and looking at the implications for storage, again, under future climate conditions. I don't have many concrete results to show, but I do want to just kind of highlight the importance of the work. I think it's key that climate and weather, especially in systems with wind and solar capacity, which is, the case today and will be more and more the case tomorrow. Those conditions are increasingly important to how you plan and operate your systems. And there's a lot of evidence that extreme weather events are occurring more frequently with more severity. And so traditional modeling that kind of relies on historical weather conditions and kind of a persistence approach and assumes that they'll be roughly similar in the future, may not be appropriate anymore. And so this project, what we're doing is pulling data from climate models that has been downscaled to kind of 12 by 12 kilometer resolutions. This is coming from the environmental science folks at Argonne who do a lot of kind of detailed climate work in this area. They have tons and tons of data, close to a petabyte of data related to different weather variables and different future projections. And what we're doing is trying to translate those kind of raw weather variables into identify which ones are important and influence grid planning decisions and translate them into the types of inputs that are used in planning models for the grid. The key ones being, temperature, global irradiance for solar, wind speeds, and things to that effect. So what we've done, and I show this because I think it's a really, kind of interesting demonstration of some of what we've been able to do. But this is a climate simulation from 2093. So obviously, no one is going to say that like on this hour, on this day, we're going to see these conditions. But it is really interesting that our researchers who are looking at this actually found a hurricane occurring in Texas that coming out of the climate model. So it's able to capture those types of conditions and identify periods where they're potentially more likely to occur or occur with higher frequency or higher kind of more impactful magnitude. I do want to highlight, while this is kind of an eye-catching image, actually for long-term planning, I mean, we're definitely interested in these types of conditions, but maybe more impactful to planning decisions kind of prolonged periods of intermediate conditions. So prolonged periods of, week-long periods of very high temperatures in the Southwest or in Texas that we've been seeing in recent years that are only going to get more pronounced. And those actually might have more implications for, say, longer duration storage technologies where you really need, multiple days of storage to kind of support the system through those types of periods. So this is getting a little bit deeper into methodologies, but what we're planning to do is incorporate some of these data into our models, develop a more of an updated approach for selecting the representative periods that we use to capture future conditions, conduct some more stochastic oriented, like probabilistic modeling to kind of understand the implications in the future. And again, specifically looking at different long duration energy storage technologies. So again, stay tuned for more on this. There's a lot going on in this field, both at Argonne and, a number of other labs I know are heavily involved in this as well. And that's all I had prepared today. So it's a bit of a whirlwind. I think I just about stuck to my 15 minutes. But yeah, happy to answer any questions or, provide more info offline if that's helpful.
Awesome. Thank you so much, Todd. That was a great presentation. Yes. Good job on time too. Thank you for that. We're running a little bit ahead of schedule, so we'll take some time. We'll take some time to do some questions here in the chat. Looks like I got one from Brian Evans Mangion from the village of Hyde Park, who asks, has your group looked into any aspects for power accounting within ISO markets when charging and discharging uses occur, or as to how such uses will be treated in renewable or clean energy requirements?
So let's see, accounting. So I might need a little bit clarification. So on how the charging and discharging of storage accounts towards clean energy requirements, is that the main question, or how it's like netted out? I'm not quite sure I'm following the question, but
sure, I believe so. But Brian, if you're on the line, feel free to actually come off mute and clarify if you don't mind.
Oh, here's the question. Power accounting. So I think, in terms of how storage is treated for renewable and clean energy requirements, generally, the act of charging or discharging is not counted. What matters is what energy is being used to charge. So, when it's charged. So if storage is charged from excess solar capacity, it means that solar generation is happening and it's being moved through time to a later period. But I don't think there's generally accounting of it gets counted because that solar generation occurs in the initial period. So I don't think it's necessarily counted when the storage is dispatched in the later period, if I'm understanding correctly.
Well, Todd, this is Brian.
Yeah. Okay, great. Yeah.
So, yeah, I mean, that's part of the question. I mean, what happens is that depending on where the storage device is located, whether it's co-located, then obviously you can dedicate the output of the plant to that particular solar site, and you can get a proper accounting of what feeds what from one goes to the other. But when you have more of a storage facility that is out on the grid, okay, how do you track where the energy is coming from that is going to go into the storage unit so that when it gets discharged, and if there is an accounting for the unit as a result of any renewable requirements or clean energy requirements, how do you track the attributes in order to ensure that there isn't double counting, that there isn't, some consideration of the type of energy that's being used to store versus what's coming out in these other programs. I know it's tangential to the value of storage, and don't get me wrong, I recognize the value of storage, but I think it's an important aspect as to how people are going to use storage going forward.
Right. Yeah. So let's see, a couple of thoughts. I don't know if this is going to quite answer the question, but other than to highlight that I think it is a major challenge, and that gets at a little bit of the jurisdictional issue I highlighted at the beginning. So, for example, if you're in like a PJM in a large multi-state market, you have a storage device located in one state. There's excess solar capacity in another state, and you kind of use that to charge, and then you dispatch that later in your state. Yeah, what is the accounting for how that which policy target that gets counted towards? I think traditionally it would get in a market setting like that, it would get counted at the point of generation, is my understanding. And so unless you have some sort of system in place to sort of track, but in a market framework, you could track based on whatever kind of the marginal unit is at the time, but there is no it's kind of linkage between a specific storage facility and a specific renewable facility, unless you're operating as a hybrid, like you're saying. So again, I guess I will just reiterate that I think that is a challenge, and because of the way policies are designed and oriented, oftentimes by there's not that much coordination between like market operators and policymakers at the state level. It creates some of these challenges that could, in theory, be addressed by like a more cohesive regional or federal policy that isn't not always politically feasible.
Thank you for confirming the nuances that I was having trouble with.
Okay.
Appreciate it.
Sure.
Great. Thank you both, Todd and Brian. Appreciate that. Looks like we don't have any other questions for you in the chat, so I want to give another hand to Todd. Thank you for stepping in and presenting for us today. It was a lot of information, really good information. Again, everybody, I encourage you to reach out to Todd should you have any more questions that occur after the presentation today. With that, I want to go ahead and transfer to Patrick Balducci from Argonne National Lab. Patrick, let's see, you just joined. Hey, how's it going?
Hello.
And are you able to share your slides, or would you like me to do it?
Yeah, I think I can share my slides here if we just take
Great.
a moment. Here we
course.
go. Yep. So,
The floor is yours.
Great. Okay. Hi, everyone. Hold on. Let me see if I can share here. Okay. Then I'll bring this up, and then I will do this. And then tell me if everyone can see the slides and me.
Yeah, looks great.
Okay, great. So yeah, usually I go first, and this is sort of the energy storage valuation 101 before you get into some of the other thornier topics. So sorry that I'm going last. We had some DOE dignitaries here on site at Argonne, and so I was spending the day with them, and we're also having an energy storage conference on site here at Argonne. So it just wasn't the best timing. But I'm happy to be here, and we're going to go over a few things, just sort of the fundamentals. What is the value proposition for storage. What are the basic values that are derived from energy storage? And then we're going to get into, at least showing you how some of these different value streams are brought together, co-optimized, so that we can get a better and fuller understanding of the benefits and costs of deploying energy storage. So what you see on your screen here is that a taxonomy that we developed a few years ago when I was at Pacific Northwest National Laboratory, where you can see that there are bulk energy, ancillary services, transmission services, distribution services, customer services. Maybe a sixth category I would lump in there would be reliability services. So you can see the types of services that are offered by all forms of energy storage. So bulk energy, capacity, and energy arbitrage, which of course is buying low and selling high. When you're dealing with vertically integrated utilities, then those are avoided costs, right? You're basically peak shaving and then charging up in the middle of the night when the costs are low. When you're dealing with the market, you're buying low and selling high in the market. Ancillary services, making sure that supply and demand or load and generation are always linking up. And so you have frequency regulation, spend, non-spend, typically within markets, frequency response. NERC BAL 003-1 requires if you're connected to the grid that you must respond to significant sags in voltage. And so there are utilities across the country that are required to effectively inject large amounts of energy back into the grid on a moment's notice. And but the actual value of that is very, very dependent on the specific utility. The utility typically will provide this service, but in some cases, they are signing contracts with third parties to transfer the obligation. Their, black start service, basically re-energizing the grid, flexible ramping in California ISO, voltage support, transmission services, basically upgrade deferral and congestion relief. And then at the distribution side, it's basically voltage support and then distribution upgrade deferral. We conducted a really extensive literature review and then segmented the values in terms of dollars per kilowatt per year by region. And you can see, although that energy arbitrage is, the value that's most commonly tied to energy storage, it actually is one of the lower values, as you can see here. Of course, it varies by region. Capacity a bit higher, but capacity is uncertain. So if you're bidding into a forward capacity market, and you're counting on capacity revenue over the economic life of the unit, you see large fluctuations. ISO New England was trading at about $11 per kilowatt per year and got down to, or I should say per month, and got as low as I think $2 or $3 per kilowatt per month. So significant decline in terms of the value as more entrants to the market shift the supply curve and the prices come down. Frequency regulation tends to be a higher value stream for battery storage. Transmission and distribution values are lower in terms of the number of projects that can take advantage of them, but in some specific locations, the values is actually quite high for specific projects. We're going to highlight one of those projects in your region today. Frequency regulation, ancillary service markets are very shallow. So for storage systems like pump storage hydro, most of the value will be tied to capacity and energy arbitrage. I'm talking about 80 to 90%. Because if you've only got a 400 or 500 megawatt market like for frequency regulation, like the MISO market, then bidding in a 1 gigawatt plant into that system effectively crashes the prices. So you're only going to get value associated with a segment of your capacity, and certainly not all of it. Okay, so some of the challenges to accurately estimating economic benefits of energy storage. There is multi-dimensional competition for the energy in an energy storage device. If you offer it in 1 hour, there's less of it available in the next. And of course, you cannot satisfy all of the requirements of all of the services simultaneously. And so you need, when determining the value of energy storage, you need sophisticated models that can simulate the co-optimization of services subject to the technical limitations of the energy storage systems. You cannot serve all services simultaneously. And so effectively, optimization algorithms are used to determine which service is highest value, and then how you effectively operate between those services over time while accounting for the value of meeting all the needs of those services, either as defined by the market or by the grid system itself. There are a lot of challenges in doing this, and of course, when you're dealing with these valuation tools, things like perfect foreknowledge of future systems effectively can lead to overstatement of the benefits. And of course, if it's a large-scale energy storage system, you would influence prices within that market. And so there are now market simulation tools and price influence or system simulation models that can be deployed to create more realistic estimates. Also, advanced sort of statistical techniques for bidding the system into the simulated environment can be used to acquire more realistic estimates. Economic results are sensitive to sizing. So you can see the results of one of the studies that we conducted in the lower left. And it was a very shallow system with an energy to power ratio of 0.25. So you can see that the costs exceeded the benefits. The return on investment ratio was below 1, and the results were suboptimal. But if they had right-sized the energy storage system, in this case, with an energy to power ratio of 2, it could have yielded a positive economic returns. And so performing these analyses before you actually deploy the system is the better outcome in this case. Right sizing it, getting the right system, and then putting together control systems that will take advantage of these the economic landscape of economic opportunities is very important. Understanding the full capabilities of the system and accurately understanding the efficiency of the system is very important. We found that there were systems that were deployed with stated efficiencies of about 90% by the manufacturer, but then when operated and accounting for economic operation, which might be less than optimal, and taking account inclement weather that can drive down the round trip efficiency, and for auxiliary power flows and HVAC systems and power conversion systems, the actual efficiency rating was quite a bit, sometimes 10 to 15 percentage points below what was estimated by the manufacturer. Also, understanding degradation is important. You don't want to overcycle the systems. Typically, they're operating within warranted limits, but understanding the effects of degradation and what drives it is important to getting an optimal outcome. Okay. So some of the simple use cases, the value streams, capacity or resource adequacy. In most parts of the country, there are forward capacity markets into which you can bid, and then effectively the system must be there and available for providing typically up to 4 hours of continuous service during those peak periods, and for that you're paid a fairly significant amount of funding. It's based on the cost of a new entrant, typically a peaking combustion turbine, with adjustments for the flexibility benefits of that turbine, and then also the incremental capacity equivalent of the energy storage system. So, if the value of the service is roughly, let's say, $50 per kilowatt per year, and you're operating it with a 2-hour system, you would be dividing that value in half effectively, because you have to provide 4 hours of continuous service. Frequency regulation. This is the second by segment adjustment in output power to maintain grid frequency. There's three components to it. Capacity, so you're bidding in a regulation capacity clearing price. Mileage, so as you can see in the chart there, that as you cycle energy into and out of the battery, and the battery set point shifts up and down, those green bars, the sum of those green bars form what's called a service payment or a mileage payment, and that drives an outcome as well. And then finally, battery storage systems receive, as all those who bid into this market receive a performance score. Battery systems score very high typically, and so you retain much of the value that you acquire through the provision of this service, where some generators and assets that perform less well will face a more significant deration. What we found in the PJM and some other markets is that when a significant energy storage is bid into the market, they perform at a very high level. Their ability to actually satisfy the requirements of this market and accurately follow the signal are exceptional. And in so doing, they generate value to the grid, but actually undermine their ability to obtain revenue because the market can actually crash as the requirements for this service are satisfied by the battery systems. And so it's important to understand some of the variability in the future revenue potential for this. And so while it is a high value stream, the value stream over time is uncertain. Another value stream for energy storage, of course, is outage mitigation. We've recently completed an analysis of the outage mitigation potential of two battery systems plus tidal energy plus community solar on the San Juan Islands in Washington State. And you can see where we segmented the island's grid. It's connected to the mainland Washington State with two submarine transmission cables into four different zones, and then matching those assets with those zones and the outages that took place. Effectively, you can island the islands in this case, and basically all you really need to define the value. Well, there's two really levels of sort of analytics that you could employ here, but the most simple, of course, is just knowing the customer counts, knowing the loads on each of the segments that you'll be islanding, knowing the assets that'll be brought to bear, and then effectively weaving those into an optimization tool, and then simulating historic outages, and then determining the value through the application of value of lost load data that we acquire through the Lawrence Berkeley National Labs interruption cost estimator, which is built on a series of interruption cost studies that they have performed. And so by the simulation of these outages, you can figure out the value of lost load with and without the presence of energy storage. And the marginal value, of course, is the value that's attributed to the presence of energy storage. From the utility perspective, there would be energy sales during those outages that would have otherwise not taken place. And also, there can be penalties associated with low levels of reliability, and there's value associated with that from the utility perspective as well. If you want to get into much more sophisticated modeling, you can get into the distribution level modeling, using models like OpenDSS or GridLab-D to better understand the use of energy storage for realizing those outage mitigation benefits. And when we've done that in the past, you find out that specific areas might require reconductoring or some other automated feature switching and other elements to actually generate the full value associated with outage mitigation. So those more sophisticated modeling techniques will give you that level of information. Transmission and distribution deferral, fairly straightforward, either because of declining infrastructure or because of load growth. Investments are required at either a distribution or transmission level. From an accounting perspective, for the utility, effectively the cost of the system will be higher as you defer investment in that system into the future, but When you're discounting it back, typically in the denominator of that equation will be the weighted cost of capital, which generally speaking will be considerably higher than the inflation cost. And so you can see taking the 10 million for a distribution level investment, 1.03 raised to the sixth power, divided by 1.08 raised to the sixth power brings that value, or that cost in present value terms, down to 7.5 million. The difference being 2.5 million. So that's the distribution. That's the benefit of distribution deferral in this example, which comes from a study that we conducted on Bainbridge Island for Puget Sound Energy. Similarly, we conducted a study for the Orcas Power and Light Co-op, and then also for National Grid on Nantucket Island, where the cost of the submarine transmission cables were much higher. Nantucket Island, you'll learn more about in just a moment here. Something that we've been exploring, which is a really key component of energy storage value, but heretofore really hasn't been valued very concretely or comprehensively or consistently, is resilience. So resilience benefits, typically evaluated using customer damage function, so the value of lost load. But others have attempted to use willingness to pay studies. So effectively, you're asking different consumers how much they'd be willing to pay to avoid outages. Also, input-output analysis has been used, or computable general equilibrium models by economists to understand both the direct, indirect, and induced effects as those outage costs cascade across an economy. What we have done is, I first wrote a paper about it, which is cited below, and then found the models to actually carry it out. And we're going to be doing this in at least one study, and perhaps two, that we're being funded to do here in the next year to 2 years. And basically, what we're applying is an annual risk premium. Think of it as like insuring a utility against the fallout from low frequency but high impact outages. So we're tying together multiple models. So we're taking risk profiles associated with weather events, human risks, and determining the expected value associated with those events on an annualized basis. So it's going to be based on the probability of those events occurring, and then the costs associated with them occurring. And we need a series of models to determine those values, because we have to assess the impacts of those threats to the grid and to individual customers, and then the recovery times that would be tied to those events, both with and without either the investment in transmission capacity or long duration energy storage, for example. And then the difference between those, once again, annualized. So if it's expected to occur, say, every 10 to 15 years, if you know the probability of it occurring, and then if it does occur, that the cost is going to be, say, 100 million or 150 million, then you can annualize that risk. And so that's what we're going to be working on doing. So each of these are translated then into an annualized risk profile and a risk premium associated with each of them. And then we're going to evaluate the grid firming effects of transmission investments and long duration energy storage. So tying these together for Nantucket Island Energy Storage System, a small resident population of 11,000, but the population swells to 50,000 in summer. So the load on the island surges. It's currently connected to the mainland Massachusetts with 2 submarine transmission cables. They were considering a third that would wind around the island and then connect at the Bunker Road substation there at a cost of $150 to $200 million. We're employed by National Grid to evaluate the transmission deferral benefits of it, but also the benefits in terms of improved reliability and participation in the ISO New England market. And what they were investing in, instead of investing in that $150 to $200 million submarine transmission cable, they chose to invest in a combustion turbine generator, 16 megawatt is its maximum capacity, and then a 6 megawatt, 48 megawatt hour Tesla lithium ion battery energy storage system. So we did a thorough analysis of load, sort of stressed out that load in sort of an extreme weather event, and then forecast that load into the future to determine how long the deployment of these local assets could maintain that N-1 contingency capacity in the event of these sort of extreme load conditions. And we learned that we could reasonably expect the load or the investment in the submarine transmission cable to be deferred by roughly 13 years. We also performed distribution analysis. We modeled the distribution system on Nantucket Island using GridLab-D and OpenDSS, and simulated the outages that took place over an 11-year time horizon, which I believe were something like 700 outages. It was quite a significant number of outages. And from that, valued the investment in these assets. As we did that, we uncovered the need to make additional investments in the distribution system, and we could show the marginal positive value of making those investments and wove those into the analysis as well. And you can see the value of local operations being estimated about 122 million, which that alone exceeded the revenue requirements for the CTG and the energy storage system, which was $93.3 million. We then simulated market operations using the continuous storage facility option for ISO New England. Rather than assuming perfect foreknowledge, we built in using a small number of statistical techniques and evaluated each of them, and then settled on one. I think we used the gradient boosting machine method, but we also evaluated the ARIMA method as well. And so what our model was doing was simulating, sort of market operations, and then first bidding in to the market, and then settling in terms of the value based on the actual market prices. So we used historic market prices, but effectively extracted that perfect foreknowledge problem by modeling it as though we were bidding into those prices without any foreknowledge. And from that, we derived an additional value of about 24 million in present value terms, most of it tied to frequency regulation. So when you added them all together, you can see a total value of 145.9 million compared to 94 million in costs. Return on investment ratio of 1.55, which means that for every dollar of investment, one could expect $1.55 of returns. Once again, the biggest use case was the transmission deferral use case, but also significant outage mitigation or reliability benefits, and also significant benefits associated with providing frequency regulation. You'd be correct in noting that there are challenges to actually doing this because this would have been rate-based, but there are opportunities to propose these sorts of investments, and a memo had been issued by FERC, I believe, governing this investment. And so we were basically defining the value proposition of trying to pursue this with the idea of bringing the value back to the customers through the reduction in future upward pressure on rates. We've modeled Northampton microgrid, and for many of you, you're probably well aware of the structure of the local charges that large commercial and industrial customers accrue in the Northeast and in New England. And if you can shave peaks, you can accurately estimate when distribution and when transmission peaks are occur, then through the ICAP and the demand response programs, you can obtain significant value. So what we were showing there was by tying together, all of these assets, which would include solar and multiple investments in energy storage. The idea was to bring the Department of Public Works, a local hospital, and a local school, which would act as a Red Cross shelter, together. That you would greatly improve reliability. So with a full microgrid and full sharing between microgrid members of loads, so effectively you're operating as one, whole unit, that all of the outages that we modeled that they could withstand those outages up to 7 days. In the absence of the presence of all of these assets, and only using existing assets, which include generators and one small solar unit, the failure drops significantly. So you can see 40 to 89% in the scenarios that we ran. And of course, 14-day outages, the survivability drops significantly. But basically what we were showing is that you could greatly improve reliability, and then these systems could pay for themselves. Okay, so something we worked on, my team worked on when I was at Pacific Northwest National Laboratory, was taking an enormous amount of test data and then modeling energy storage. And what we found there, as I mentioned previously, is that not only is there
Hey,
is
Patrick,
run
just a quick time check here. You just got about 5 minutes or so left as we're
Yep.
running a little short of time. Thank
Yep,
you.
absolutely. Absolutely. Yep, I'm going to wrap it up here in just a moment. So not only was the round trip efficiency lower than what the utilities were expecting when they deployed the systems, but that it was highly variable and dependent on chemistry. So, for example, we explored vanadium redox flow batteries, and their round trip efficiencies could vary from, say, 60 to 85%, depending on the operation. So the depth of discharge, whether you were charging or discharging or power output level, temperatures, and state of charge, all dramatically affected the efficiency rates. And so what we found is that, and what this chart is showing is that our projected efficiencies and actuals would deviate significantly at the beginning of a testing period, but then we would model the system over time and then greatly improve our ability to estimate that. So this is just a note that we do get a pot of funds from the US DOE each year to evaluate novel energy storage deployments to help utilities and other partners across the country to expand the use cases for which energy storage is deployed and better understand the value proposition for energy storage, the combination of energy storage with many other assets. We explore all of those things. We have this pot of funding. So if there are people in the audience who have interesting energy storage projects and need help in understanding the value proposition, there may be an opportunity for us to work together. The last 3 slides I was just going to note very quickly. We have a suite of energy storage valuation tools, but in addition to Argonne National Laboratory, here are some energy storage evaluation tools from our sister labs and from EPRI, energy storage evaluation tool, DERVET, Quest, and Reopt Lite. And I'll just cut this short to say, obviously, ESET and DERVET of these 4 systems, easily the most comprehensive in terms of use case coverage. Quest is very good at exploring market benefits at locations around the United States, and they have a database that allows you to do so rapidly. The use case coverage is less, but of course, market services are more limited than services that a vertically integrated utility would have. And so Quest is very good for those market assessments and user-friendly, and the data is there for you. And then Reopt Lite is really focused on microgrid assets. So a microgrid evaluation tool, now ESET has a microgrid evaluation tool, but if I had to kind of focus on what's great about each of these tools, I would say ESET and DERVET are the most comprehensive in terms of their coverage, Quest, market analysis, and Reopt Lite for microgrid evaluation. So I've kind of covered, many of these, but these are some of our conclusions. Performing these techno-economic assessments before you deploy the energy storage systems are very important. We have found significant mistakes made by utilities that deployed them without performing a comprehensive techno-economic assessment. It's important to consider a broad set of use cases, but typically in operation, it's going to be a small subset of use cases. You simply are not going to provide 10 different services simultaneously. It becomes an intractable problem and difficult to manage. Significant regional variation, even within a region, if you're a PUC versus a vertically integrated utility versus another utility that's spitting into a market or a military base with a microgrid, the value streams will look very different. Same thing with respect to utility structure, and then understanding your battery performance and degradation is key to a positive outcome, because the economics are driven, and not only by the landscape of economic opportunities, but also the capabilities of the energy storage system and how robust it is. And so these are all key considerations. With that, I just would like to acknowledge, Dr. Juk and all the other fine people who contributed to this presentation, including those at the other 3 national laboratories I contacted to learn more about their tools. So with that, we probably don't have too much time, a minute or two, if you have any questions.
Awesome. Yeah, thank you so much, Patrick, for that great presentation. Really appreciate that. I do have a couple of questions here in the chat, so we'll try and do 1 or 2, time permitting. I do want to start with our friend Charlie Vartanian from IEEE, who asks, do you have any guidance? Oops, where'd it go? Do you have any guidance on bridging capacity terminology use difference between traditional power industry, like capacity is power, kilowatt, megawatt, gigawatt, and energy storage community that sometimes uses capacity in context of energy storage capability or rating in kilowatt hours, megawatt hours, or gigawatt hours?
Oh yeah, I mean, first of all, I say hi, Charlie. Now, I mean, when you think about capacity, I always think about it in terms of power and energy capacity, of course, and so that's very different. So, how much can you push out of the battery system at any given point in time? But also, how much energy can you push out of it, and which are separate. And something I would just note about that is that we found with some of these energy storage systems that they are not necessarily. So, if you have a 1 megawatt 4 megawatt hour battery system, you would think that our capacity is 1 megawatt, but we have 4 hours of energy stored. That may or may not be true. We found with some of our battery systems that if you actually discharged at 1 megawatt for 4 hours, you'd be totally discharged after, say, 3.2 hours. So what you really had was you kind of had either you had a sort of a 4-hour 800 kilowatt battery, or you had a 6-hour 650 kilowatt battery. So understanding it in terms of hours is not necessarily accurate. But yes, you measure power and energy differently, and you must understand that they are separate, and you cannot necessarily assume that discharging at full power for 4 hours will get you that. And they find that also when they are bidding into capacity markets, they have to demonstrate the capacity to deliver that over 4 hours. So if you've got a 1 megawatt, 4 megawatt hour battery, it could be that you're only going to get 800 kilowatts of capacity revenue. So I don't know if that fully answers your question, but that's just kind of my exploration of the topic.
Thank you. Helpful insights.
Thank you, Charlie. Nice to hear from you.
All right, moving along, I got another question for you from Vidya Venkayala from the British Columbia Institute of Technology, who says, thank you for elaborating on resilience valuation. Is there also a method for comparative valuation of storage duration versus density/form factor? For example, valuation of long duration, larger footprint battery versus shorter duration but compact lithium battery?
Yeah, I mean, and the question, you could take that many different ways, but each battery system has this is the way I'll answer that, is that we recently worked with McKinsey to develop this long duration energy storage. I'm trying to remember, commercial liftoff study, and a few notes about that are that when you look at the markets, right? So some energy storage systems will be needed for ancillary service markets. So that's a fast acting, high performance driven market. Others are more focused on diurnal energy shifting, so peak to off peak. Others can be multi-day. Others could even be interseasonal. So the first point I would make is that the systems themselves, you model the characteristics depending on the landscape of economic opportunities. One will benefit relative to the other. So in some cases where you're focused on certain reliability, resiliency, and other benefit streams, there perhaps capacity in some others, you're going to need that longer duration. And I refer back to my graph where we showed ESET, for example, and our models can do the same thing, can define the optimal energy to power ratio to take advantage of that opportunities. But then secondly, I would also note that basically when we think about commercial liftoff specifically for long duration energy storage, if it's a diurnal market, maybe you're more looking at like pump storage, hydro, maybe compressed energy storage versus intraday, versus seasonal. Then you start getting into, flow batteries start factoring in there, but then ultimately there's new technologies that are being developed, and of course hydrogen and some others. And so as you start thinking about what it is that the energy storage system is needed to do, if it's solving a valley of the death when the renewables are not producing, or if it's simply shifting energy around diurnally from peak to off peak, you're looking at different energy to power ratios and frankly different chemistries that will be required to, or different types of energy storage to achieve the needs of each of those different sort of tranches of investment.
Great, thanks for that. Looks like we got time for just this last question. Doug Hurley from the Ice Tech Energy Services asks, have you thought about or analyzed the value of a long duration BESS contrasted with multiple short duration, like lithium, BESSs that could be dispatched either simultaneously for higher power and short durations or sequentially for lower power for longer durations?
Mm-hmm, mm-hmm. The answer is no, in the sense that we have not completed any project that addressed that specific question. It is a very interesting question though, but I have not tackled that question. Thank you.
Great, and thank you. And I just want to give a big hand to you and to all our other presenters today for giving such great presentations on the content provided. So thank you all, and I will turn the table back over to John, who can close us out for today.
All right, thank you, Dylan. So that concludes our third session in the 5-part series. I want to thank everyone for attending, and excuse me, all of our presenters, especially we had some, as was mentioned earlier, we had some folks stepping into pinch hit here. We had a last minute unfortunate cancellation by Mr. Clark, who we are hoping to be able to work back in, perhaps in the next session on November 30th. Again, I would like to thank everyone from Sandia and Dylan, of course. Again, thank you so much for running the platform for us today and keeping things going smoothly. We will be pausing next week for Thanksgiving, and we will resume the series with our 4th session on Thursday, November 30th, again, from 1 to 3 p.m. Eastern Time. Our 4th session will address the aggregated operation of storage facilities, both in the context of multiple storage facilities and storage coupled with generation. More detailed information on next week's agenda, as well as the agenda for all remaining sessions, can be found in the Commission's order announcing the series using the Commission's online case management system, EPUC. The document can be found in EPUC at case number 21-3883-rule and selecting the Commission Issued Documents tab, and then selecting the document dated September 29th, 2023, titled Order Announcing Webinar Series. Also, as I mentioned earlier, under that same Commission Issued Documents tab, you can now find a memo with a link that will take you to the audio and video recordings from session 1. And using the All Other Documents tab, you will find the 3 slide decks from our first session as well. The remaining videos and slide decks will be posted as soon as they become available, and you can just use that exact same process to find them, and you'll just have to look for the correct date and the document title for those future postings. So again, thank everyone for their attendance today, and we hope to see all of you again on November 30th, and hope that you have a relaxing long weekend next week. Thank you very much. We're concluded.